This video right here is we're gonna be talking about linear approximations. This is one of two of the videos that I want you to watch over the Thanksgiving break. So go ahead and put this in your table of contents. We're gonna talk about linear approximations and how we calculate values before the use of technology, really, how values were calculated and kind of approximated. Standard is AD1. We're still talking about tangent lines and tangent lines and slope. This is page 120. These are the notes that you got on Friday before the break. So this target is students will find the equation of the tangent line using the derivative process to estimate an unknown value. Remember, when we talk about our derivative process or using our derivative process to find the equation of the tangent line, that's always 4 steps. I'm going to review that really quickly. Our first step is always find our y. Second step, find the derivative. Our dy dx, y prime, whatever you want to label that as, f prime. Third step is plug into the derivative to get slope. Remember that derivative represents the slope of the tangent line on the slope of our curve. And then 4, write the line. And again, remember that the form that we use is point slope form, and you're going to see why this form is the most important form. Remember, we always solved out for y, so m times x minus x1 plus our y1. Okay, so we're going to use that point slope form. And it's going to become clear why that form was the best form to use in our class, specifically for this process. Okay, so the idea of a tangent line. So let's say we have a function f of x in our graph, and then we have the tangent line. We're going to label that L of x. We can write the equation of a tangent line by using this formula right here, or right here. This is the form we use, that second one. If we think about it, this is just a fancy way of saying y equals my m, my slope at that point, x minus my x1 plus my y1 at point a, f of a. Okay, so it's the equation that we're using. And then the tangent line itself, if we think about the tangent line and we choose a point on the actual function, let me get a different color. So let's say I wanted to know that point right there, but I didn't really know what f of x was. I just knew what my slope was at that point, or at this point right here. I can use my tangent line and figure out what that point is in my tangent line to figure out and estimate what my f of x is going to be. So I can actually plug in that point, let's call it C. I can use L of C to estimate what f of C is, okay, what the y value is. And the distance between those two values right there is going to be the error of approximation. That's a terrible, let me redo that. We still with that. So that distance here is our error. Okay. So that one has quite a large error. We could always adjust our tangent line by moving our point, changing our point. Again, if we don't know the function, these are kind of how values can be calculated. And we can calculate other values like the square root of 2 using our tangent line. We can approximate it, what it is to be pretty accurately. Okay, so let's kind of look at an example. It says use the linear approximation for f of x equal to the third root of x at x equals 8 to approximate the third root at 8.1. Okay, so this is a value we can calculate. Okay. We have a value that can be calculated by simply plugging in into the equation. So if we plug in 8, the third root of 8, of course, is 2. We know that. But we can use that exact value to approximate a desired value. So this 8.1 is our desired value. So if we think about our function, here's our 8 value right here. So that's that point right there. I'm going to go slightly above. Let me get a different color. I want to use that same line to approximate about 8.1. Okay, it's going to be a really good approximation considering that that tangent line is a pretty close value. So the tangent line and the function are almost exact still at that point. So that approximation is going to be really good. So I don't know how to find the third root of 8.1, but I do know how to calculate using a linear function. That's something we learned in Algebra 1. So if I can get the equation of that line, I can actually equate that value pretty accurately. So kind of there's a two-step process when it comes to using a tangent line as an approximation. We call it a linear approximation, sometimes called linearization. But all those three things pretty much mean the same thing. And it starts with the very first thing, something that we've been doing since we started derivatives. And that's just find the equation of the tangent line. So our first step is simply find the equation of the tangent line. Okay. Again, that's something we've been doing pretty much since we started, so I'm going to highlight that. That's kind of our first step in linear approximations, is to find the equation of a tangent line, linear function. So of course, I'm going to use my four-step process. First step was to figure out our function. So f of 8. We're going to use 8. We're not going to use 8.1 because I don't know what the cubed root of 8.1 is. But I do know that the cubed root of 8, no decimal, 8.0, is in fact 2. So I have a point of 8.2. That's something I can calculate. Okay, next thing is to take the derivative. This is one that I would want to rewrite. So x to the 1/3 power, not 1/2, 1/3. So 1/3 x, and we subtract 1, basic power rule, we get negative 2/3. Now I'm going to be plugging into this, so I want to definitely put it back into the proper form. No negative exponents, no rational exponents. So that negative exponent is going to reciprocate it, which means it's going to force it to the bottom. And it's going to go back into its original form, which was root form. So x squared. Okay, going back to just basic power rule. Our next step in the equation of the tangent line process is to plug in our value, same x value, to figure out our slope. Remember, our f prime is just our slope. We're taking the third root of 8 squared. Okay. Remember, with roots and powers, we can do them in any order. So I can square first. 8 squared is 64. And then know that the cubed root of 64 is 4. Or I can cube root the 8 first, which I already know it's 2. And then 2 squared is also 4. So the same result comes out whether we do the root or the power first. So we wind up getting 1/12. Okay. And then, of course, the last step is to actually write the equation of the tangent line. Okay, this is nothing new. We've been doing this since day 1 of derivatives, not 2. Sorry, I made a mistake there. That should be 8, and then plus 2 here. Okay, so that's kind of the first step in using a linear approximation or finding a linear approximation. Our second step is to plug in the desired value. And I just noticed that I wrote derives, not desired. Sorry for my moment of terribleness. So I'm going to erase that really quickly. Let's pretend that that didn't happen. I know there's proof now that it's on video, but the desired. That's better. I know I said desired, but I wrote derived. I don't know why. Just pretend that never happened. Okay, so we want to plug in the desired value. Okay, into our tangent line. Okay, remember the whole point of an approximation is to calculate a value by hand that we can't calculate without the use of a calculator. So yes, we have a calculator now, but this is kind of the process that was used before the invention of technology and the power that you guys have in your hands now. Okay, so we're going to take our tangent line. Remember, we're looking for a y value, an f of 8.1. Okay, so we're going to plug in, so 1/12, and then the desired value is at 8.1. So we're going to plug it in for the x, and then use that to solve for y. So we get 1/12 times 0.1 plus 2. Now, if you don't know what 1/12 of 0.0 or 0.1 is, we could always use long division. Okay, we're taking 0.1 and dividing it by 12. So I'm going to just do some long division. Going back to middle school right here. Okay, so decimal place, 12 doesn't go into 1, so I'm not at 0. Okay, not that. Okay. Now, 12 still doesn't go into 10, so again, I'm going to add another 0, top and bottom, and then 12 does go into 100 8 times. So that gives us 96, which gives us a remainder of 4, of course, point. And then, of course, what we'll do is we'll add another 0 to get our 4th decimal place, because we like 4 decimal places. And then 12 goes into 40 3 times. That gives us 36, a remainder of 4. So we're going to get some repeated values after that. But really, we only care about 4 decimal places. So I know that 1/12 of 0.1 is 0.0083 plus 2, which gives us 2.0083, which means our f of 8.1, which is the cubed root of 8.1, is approximately 2.0083. Now, if you have a calculator, I want you to plug in and find the actual, and you'll see that it's pretty close to this approximation. I mean, it's pretty much exact when it comes to our 4 decimal places. So pause the video, plug it in, see what you get. So this particular example, they gave us the function, they gave us the value, and then they asked us to approximate another value. The next example says to use a linear approximation for f of x equal to sine x to approximate sine of 1.5. So they didn't give us a value to use. So what I'm going to do is I'm going to choose a value. Okay, so we're going to have some choice here. Choose a value for x that's close to 1.5. Okay. If that was sine of 3.5, then I would want to choose a value that's close to 3.5. If it was 0.5, then I would want to choose a value that's close to 0.5. If it was 9, I'd want to choose a value that's close to 9. Now, trig is tricky because of the fact that when we calculate trig needs to be in terms of pi. Okay. Like the sine of pi, or the sine of 3 pi, or the sine of pi over 4. It has to be in terms of pi. So if we think of pi, remember pi is approximately 3.14. Okay, so that's not close to 1.5, but if I take that and divide it by 2, that's going to be a value close to 5, or 1.5, sorry. So that's the value that I'm going to choose. I'm going to choose x is equal to pi over 2. Because that's really close to 1.5. Close enough that our tangent line is going to be really, really, really close to where that 1.5 is. Okay. So again, the first thing I'm going to do is find the equation of my tangent line. So starting with, we're going to use f of pi over 2. That's our x value. So if we plug it in, we get sine of pi over 2. Going back to our unit circle, or our hand movement that I taught you guys in class, that's 1. Okay. Second thing we're going to do is take the derivative. That gives us positive cosine. We're going to plug into the derivative. So cosine, equals cosine of pi over 2. Again, unit circle or hand trick, that's 0, so our slope is 0. So the point we're dealing with is pi over 2, comma 1. I'm sorry, I didn't write that. Our 0 is our slope. That's going to make things a lot easier for us. And then the equation of our tangent line gives us y equals 0 times x minus pi over 2 plus 1. Okay, after that, we go to the second step, which is to plug in. So y equals 0. The desired value was 1.5 minus pi over 2 plus 1. I'm not going to worry about that pi over 2 because that having a 0 slope is going to 0 it out, which means y is equal to 1. That also means that f of 1.5 is approximately a linear approximation of 1. Again, grab a calculator, plug it in, see if that value gets really, really close, and whether it's an over approximation or an under approximation. So the idea of approximation, whether our approximation is over or under is always dependent on what the shape of our graph is, and specifically the concavity of our graph. So for instance, I'm going to go to a blank page. Okay, get a Post-it note, write this on the side, do something. If we have a graph that's concave down, and we pick a point, any point on that function, let's say that one right there, and we draw in the tangent line. Okay. Any value that we choose on that tangent line or that we use it to approximate is going to be an over approximation because it's on top or over our function. So if we're concave down, that means we're going to have an over approximation. It's based on the concavity. So now we see why concavity is pretty important to us, because they can tell us where our approximation lies. If, opposite of that, we have a graph that's concave up, and we choose a point, let's say that point right there, and draw on our tangent line. Okay. Any value that we plug into that red line or that tangent line is going to be an under approximation because it's underneath our function. So if we're concave up, that means we have an under approximation. Okay, so that kind of lets us know whether our approximation is going to be over or under. It's going to be based on the concavity of the data or the function that we're dealing with. Okay, so let's go and look at it in table form. So a lot of times we use approximations when we don't have a function at all. Let's say we have a table of values. Okay, we can still do this entire process. Everything we're going to do is an approximation. So we're going to talk about how we approximate a derivative using a table. I know that's not something we've done it once, done it twice maybe, but we really haven't spent a lot of time on it. But let's say I want to estimate what the derivative of f is at 4. I don't have a function, therefore I can't take a derivative, so the only thing I can do is approximate it. And I can approximate it going back to basic algebra 1 and using our slope formula. So this is the point we want to actually use this or find the slope of. So if I want to estimate the slope at that point, I'm going to choose a point to the left and choose a point to the right and use my slope formula. Be very careful, remember it's y's over x's. So I'm going to choose 5 minus negative 2. So sorry, this is an approximation. 5 minus negative 2, our y2 minus our y1, y2, y1, x2, x1. So going back just to that basic algebra idea of slope. So 5 minus 3. We do that calculation and we get 7 over 2. So that's an approximation for our derivative at 4. That's the best we can do when we don't have a function. Okay, so now that I have a slope and I have a point, that point is x is 4. If I go back to my table, it's 3. It's that one I circled. I can write the equation of a tangent line by using the slope that I estimated in A, x minus my 4 plus 3. Okay, the equation of a tangent line. Plug it in, get our slope, plug in our point, leave it in that form. Now I can use that equation to evaluate values that are close to 4. The further I get away from 4, the worse my approximation is going to be. The closer I am to 4, the better my approximation is going to be. Okay, so I can just simply take it and plug in. So y equals, I'm going to change that into a decimal. That is a terrible 3. So 3.5, just for calculation purposes. The desired value, and I get that. So just doing some basic calculation, 3.5 times 0.3 plus 3. Now 35 times 3. Like when you're working with decimals and we're multiplying, forget the decimals, deal with the numbers. So if we think of that as 35 times 3, we get 100, what is that, 105? Okay. 105. Now, I need 2 decimal places because that's how, when multiplying, remember going back to old school multiplication, we multiply regular, we count the decimal places, and that's how many decimal places we need. So we have 2. So going back to that, we get 105, and then we need 2 decimal places, so we get 1.05. So going back to basic math. And we calculate that to be 4.05, which means f of 4.3 is approximately 4.05. If we go back to the data here, somewhere in this area, we have 4.05. And that's kind of consistent with our table because it looks like it's increasing at that point. It goes from 3 to 5. So it makes sense that it's going to go to 4.05. If we think about IVT, well, yeah, there has to be a value at which that's going to happen. It just happens to be 4.3 for us. Okay, now whether this is an over approximation or under approximation, because we don't have an actual graph, what we're going to do is just sketch out a graph to see what this looks like. So we're just going to sketch it out. That's a sketch. It doesn't have to be perfect. So let's say that's our x and our y axes. We have, if we go back to the data at the top, let's say that that's 1, 0. Let me put some tick marks. Let's say that's 3, that's 4, that's 5. Now we're going to need about 8's about right there, and 9's about right there. Okay. Then if we go to 3, we're about -2. So let's say that that right there is -2. That was 1. So we're going to have a point there. We're going to have a point at 0, 1. That's our first point. We're going to have a point at 3, -2, which is right there. Then we'll have one at 4, 3, so about right there. At 5, 5, so it's going to increase a little bit, about right there. And then we have one at 8, 6, it's a little bit higher, and 9, 7. So our function, if we do a smooth curve, let's see if I can get this nice. It's probably like that. My little point's a little bit off. Let me go ahead and fix that. Should be a little bit higher. So if we think about this graph, that's going to be like the shape of our graph. This is as of course we're assuming that more because we don't know all those intermediate values, but we're going to go with that it's a continuous function. And if we look at 4, 4 is right there. And we draw on our tangent line. Okay. Tangent line is over because we're concave down. So I can definitely say that this is an overestimate. Because I guess I'm going to start using that one. That one was shorter. There's abbreviation or shorthand for because, not abbreviation. Because I could say f of x is concave down. Okay, and that's how I know, okay, whether it's over approximation or under approximation is based on the concavity. Concave down, over, concave up, under. Okay. We can always sketch it out and draw on the tangent line, and it kind of reiterates what I just said. So go ahead and if you have time, try some of the practice behind it. It takes a little while to kind of get used to it, but it's just finding the equation of a tangent line, plugging in and calculating. Okay, so if you have any questions, you can always send me a message or come see me the Monday we get back from break. Happy Thanksgiving, everybody.